Hello everyone, welcome to my channel, The Big Boolean Theory. This video is part of a lecture series on operating systems, and currently we are on the second module of this course, that is process management. In this module, we are trying to understand how the operating system manages the CPU by providing this abstraction of a process. So within the second module, we are currently on the second topic, that is process address space. So here, through a series of videos, we are trying to understand how does the memory appear to each process. So the process address space, right? We have talked about this in the previous videos. It basically defines how the memory appears to each process. And not only that, it also helps the process to basically organize its code and data in a proper manner within the memory. So the instructions as well as data for each process are residing in the memory, and it is the process address space which gives it a certain organization. So as we already know that the process address space is organized into several sections. We have talked about these sections, right? So there is code, stack, data, and heap. So now, after studying about the code section in the previous video, in this and the next video we are going to talk about the stack section. So let us start with why do we need a stack section and what does it do in this video. So without further ado, let's get started. So let us start the discussion with this diagram, right? So as we already know, with every process, there is a associated process address space, and this process address space defines how the memory appears to that process. It also helps the process to organize the code and data in a organized way, right? So as we know that the process address space is divided into different sections, and each of these sections has a dedicated purpose. So the four major sections in the process address space are the code section, data, heap, and the stack. So in the previous video, we have talked about the code section. It is basically used to store the instructions of the process. So basically when the process is running, the instructions of the process are fetched from this code section and then executed. So now apart from the code section, the other three sections, these are not concerned with the instructions. They are concerned with the data of the process. So as we know that when you compile your source code, you get a program, and this program has two parts. First is the data and the second is the instructions. And when you run this program, that is when it becomes a process. So we have talked about how the instructions of that program are organized in the memory, that is in the code section. Now let us see how the data is organized into different parts, that is data, heap, and stack. So let's start with the stack section. So before we talk about the details of the stack, how it is implemented, first of all, let's understand the meaning of this word stack. So basically stack means, an example, you can see a stack of plates. When you put things one upon the another, then it becomes a stack. So for example, here in this example, you can see there is a stack of plates. One plate has been placed on another, and like this, when you place several plates, it becomes a stack of plates, right? And as you already know, right, from the basics of data structure, that stack is one of the most fundamental data structure that is used in the computer system, right? So the stack data structure is very similar to a real life stack. Here, instead of real life objects, we stack data on top of another, right? So this is how a typical stack data structure looks like. So here are different, let's say, elements of data. You put one element over the another, and this is how when you put data on top of another, it becomes a stack, right? And there are two major operations associated with the stack data structure, that is push and pop. So the push operation is basically when you insert any element on the top of stack, that is called a push operation. So basically the push always happens on the top of the stack, right? You cannot push the data at any other location. It always has to be on the top of stack. Finally, the other major operation is the pop operation. So basically it is the reverse of push. When you remove any particular element from the top of stack, that is what is called the pop operation. And just like the push operation, it also happens on the top of the stack. So both the operations push and pop happens on the top of stack, on one end of the stack, and push is for like inserting the elements, and pop is for removing the elements. So this was the basics of the stack data structure. And when we study about the stack section in the memory, it is actually a stack data structure only. Okay, so we'll see how it operates. So let's take some examples and see how the stack section in the memory is implemented and why do we need a stack section in the memory. So now we'll see some code examples and understand why do we need a stack section in the memory, right? So let's go through the first example. So here we have a simple code written in C, and it does basically it returns the product of two numbers. It is computing the product of two numbers. So let's go over this code line by line and understand this. So basically there is a main function, And here we are basically multiplying two numbers 2 and 3, and for computing this product we are using a multiply function. So let's come to this multiply function. This function takes in two arguments, x and y. And basically for computing the product, it is not directly doing x into y. It is following a repeated addition method. So basically there is a result variable in which we will store the computed product. So it is initialized to 0. And in order to compute the product of x and y, we are repeatedly adding x to this variable result y times. So basically you can see there is a for loop that is running for y times, and in every iteration of this for loop we are adding x to this uh, variable, that is result, and then finally we are returning the result. So basically let's say we are doing 2 into 3, so you will add 2 3 times to the result variable. And finally, in order to add two numbers, in order to do this repeated addition, we have another function, that is this sum function. It takes in two arguments a and b and returns the sum of two numbers. So the point on this slide that I want to make is that any program that you write, any piece of code that you write, is a collection of functions. And this is a very important point. So we'll see some more examples also, but if you are familiar with programming, then you know that all of your code is in some functions. That is basically, yes, there are certain variables that are outside the function, but the point is that whenever the execution is happening, it is inside some function. From one function to some other function, it jumps, right? There are a series of function calls when your program is executing, but the point is that your program is a collection of functions. Now, this point, that is a program is a collection of functions, has a very important consequence, and this will help us understanding why do we need a stack section in the memory. So let us execute this program, and while executing this program, we'll observe a property due to which we need a stack section in the memory. So let's start the execution of this code. So first of all, the main function will be called, okay. Every function I will represent by this by a rectangular block. So the first function that is called when your program starts executing is the main function. And then there is a prod variable. So this is the variable that we are going to fill. So main function calls the multiply function, right, with the two arguments, that is x is equals to 2 and y is equals to 3, right. And in the multiply function, there is this variable result which we have to which will finally store the computed product. So initially it is initialized to 0, and then it calls the sum function. It will call it y times. So here we have x is equals to 2 and y is equals to 3. So we will call this sum function 3 times. Okay, so this is the first call to the sum function, and what we are passing the result variable as well as x. So at this point result is 0. So that is why a is initialized. The variable that we pass as argument to the sum function is a is equals to 0, and the second argument is the value of x, which we are trying to repeatedly add. So the value of b is 2. So now you see your execution, as your program is executing, you have a series of function calls, and at this point none of them have returned. So main has called multiply has called sum, but none of the functions have returned, right? So now when we reach the sum function, here we'll start returning. Okay, so we have a chain of function calls in the memory, and now let's compute this sum and start returning. So what will sum return? It will return the value of 2. 0 plus 2, it will return the value of 2. Okay, so now this, as you can see, this sum function has returned, and the current value of result is 2. But here the important point to notice is that the first function to return was called last, right? So this is last in first out behavior, which is the property of a stack. So if you talk about a stack, whichever element that you push like in the last, that is the element that is removed first. So last in first out or first in last out is the property of a stack. And if we see this chain of function calls, so here main was called first, then we called multiply, and in the last we called sum. But when it is time to return, sum is the first function to return. It was called the last in this sequence of function calls. Main was called first, multiply was the second, and sum was the last. But when it comes to returning, the first function to return is this last function, that is sum. So the point is that when your program is executing, the function calls like display stack behavior, that is last in first out, or whichever function is called last, it is returned first, and vice versa, whichever function is called first, that is the main function, that will return last. So let us continue the execution of our program and continue to see this behavior. So now the first instance of sum is done. We'll call sum 2 more times. So let's call the sum function second time. So now the result value is 2. We'll have to add 2 one more time. So here we are passing a is equals to 2, that is the current value of result, and b is equals to 2, that is the value of x. So now sum will return 4. So you can see again in this sequence of function calls main, multiply, and sum is again returning first, although it was called in the last, it was the last function to be called in the sequence. So this, we are done with the second instance of sum. We'll have one final instance of this sum function call. So let us do that. So sum has been called with the current value of result, that is 4. A is equals to 4 and b is equals to 2. And sum returns again, it returns the value of 6. So again, the last in first out behavior of this function is similar as a stack. So now sum returns. We have computed the product that we wanted to compute. The for loop, this has ended. And now it is time to return from the multiply function. So the multiply function will return the value 6. Okay. So this value of result, that is 6, will be returned to the main function and stored in the prod variable. Again, if you see this chain of function call, this small chain that is of two functions, main and multiply is returning before the main returns. So again, the property that we have been observing, that the function which is called last in the sequence of function calls is the first to return, is true. So multiply returns, and finally again the last function, the only remaining function is the main. So now main returns, and thus the execution of the program is finished. So we saw that the first function that was called was main. It returned in the last, and at any point in time, if you see the execution of the function at any point in time, the whatever is the sequence of the function calls, whichever function is returning in that chain, in that sequence of functions, it was called last. So this property is very important, and this is a property that is very similar to the stack. So basically now you understand why do we need the stack section in the memory. We have to replicate this behavior, so that is why we need a stack section. So now let us see one more example and understand this and see this property in action once more. So let's go through the second example. So this is our second example. So let's go over the code here. So basically this is a program for computing the factorial of a number. So as we know, the factorial of any number, let's say n factorial is n into n minus 1 into n minus 2 up till 1. So for example, if you are computing the factorial of let's say number 4, then 4 factorial is 4 into 3 into 2 into 1. So this is how factorial is computed. So here let's go over the code. So there is a main function and we are computing the factorial of, let's say, the number 4. So this is a recursive program. So recursion is basically when a particular function calls itself. Okay. So as you see, we are computing the factorial by this fact function. It takes a single argument, that is the number n, for which the factorial has to be computed. And the way the factorial is computed is that, first of all, there is a base condition, the returning condition. The trivial case is that the factorial we are computing, the number for which the factorial we are computing is, let's say, if n is 0 or if n is 1, then we trivially know that the factorial is 1. We don't have to do any complex computation. But let's say if n is greater than 1, that is 2 or more, then in that case we use this formula, that is, and we are returning n is equals to n factorial is n into factorial of n minus 1, right? So n factorial can be written as n into n minus 1 factorial. So this is where recursion can be applied. So in order to compute the n factorial, we have this function call, that is fact of 4, and in order to compute 4 factorial, we can compute it as 4 into 3 factorial. So see how the recursive function is being used to solve this problem. And again, the point to note is that any program is a collection of functions. And now with this example, with this recursive example, we are going to basically see the same property, how the function which is the last one to be called in the sequence of function calls always returns first. So let us start the execution of this program, and by the execution we'll observe this property. So the first function that is called is the main function. It has this variable result in which we will store the factorial 4. So main calls factorial function with the argument 4. So this is the instance of fact, and it has been called with the argument of 4, x is equals to 4. So the way we will calculate 4 factorial, as we have already seen, this is not hitting the base case, it will go here. 4 factorial can be computed as 4 into 3 factorial. So 4 factorial will call 3 factorial. In a similar way, 3 factorial can be computed as 3 into 2 factorial. Still we haven't hit the base condition. And finally 2 factorial can be computed as 2 into 1 factorial. Now we have hit the base condition. So you see, when we call fact of x is equals to 1, that is when we call the factorial function with the value of x is equals to 1, then we reach this condition and it will return 1 trivially. We will not go further into this recursion. So now this instance of factorial function with the value, with the argument x is equals to 1, this one will return, and you can see the property that we have been talking about. The first function to return was called last. Last in first out behavior. This is exactly similar to the stack behavior, how a stack data structure behaves. Okay, so if you see this chain of functions, fact of x is equals to 1 was called in the last and it is returning the first. And the same will happen for all of these function calls. So let us return through the entire sequence. So when 1 factorial returns, we can calculate 2 factorial. 2 factorial will return the value of 2. Again, it is returning last. Yes. So now after 2 factorial returns, we can compute 3 factorial. 3 factorial will return the value of 3 into 2, 6. So as you can see, again in this small chain, the size of the chain is reducing, but the property, the invariant is that the last function, the function that is returning, the function that is returning was the last one to be called. So fact of x is equals to 3 is returning, and in this chain, it was the last one to be called. Finally, 4 factorial can return. It will return the value of 24 to the main function, and when it returns, the property remains true. And finally, when the main function returns at any point in time, at any sequence of function calls, right, this invariant always holds true. That is, the first function to return was called the last in the sequence. So let us summarize all that we have learned and finally come to the answer of the question that why do we need the stack section in the memory? So we have started with this observation that any piece of code or any program that you write is a collection of functions, right? We have seen two examples, and you can think of this that any piece of code that you're writing, the execution always happens inside some function. There are several functions, right, that constitute a program. So the next consequence of this is that when a program is executing, basically execution of a program means execution of a sequence of functions. So we saw the examples, right? In the factorial function, there will a sequence of functions, right? Different instances of the factorial function. In the first example also, we saw that main called multiply, multiply called add. So if you observe carefully, any program that you write is a collection of functions, and when it is in execution, there are a chain of function calls in the memory. Finally, we also observe that this sequence of functions show stack behavior. That is, if you consider the chain of function calls, then the function which is called the last in the sequence will always return first, and vice versa. The first function which is called, let's say the main function always returns in the last. Although it is called in this sequence, it is the first function to be called, but when it comes to returning, it will always be the last function to return. Just like in the stack, the first object, right, that is pushed, it will be popped the last, and finally the object that has been pushed the last in the sequence of the stack, it will be always popped first. So that is how the chain of function calls or the sequence of function calls displays the behavior that is exactly same as the stack. Finally, the last consequence is that we need a stack in memory to support execution of functions and especially recursion. So basically, when the program is executing, we have to execute all of these functions, and in order to replicate this behavior, we have to maintain a stack in the memory. That stack section in the memory will be dedicated for the execution of functions. As the function calls happen, we will push basically we'll push an object that will be representing the function in the stack, and as the chain grows, there will be several objects in that stack. So basically, in the next video, we will talk about how a function is represented by a stack frame, and that stack frame, basically there are several stack frames that are used to like simulate the execution of the program, and that is why the stack section is used. That we will talk about in the next video, but the point is that your program is a collection of functions, and when it is executing, we have a sequence of functions in the memory which display stack behavior. That is why in order to execute the program, in order to simulate that behavior, we need a stack section in the memory. So you understand why do we have a dedicated stack section in the process address space that is basically reserved for the execution of functions. So we have just discussed that why we need a stack section. We need the stack section for the execution of the functions. So this is the process address space, and here we have the stack section. So this region in the memory is dedicated for the use of basically executing the functions that are there in your program, right? So this was the first point. So let us see some more points about the stack section. So the second point is that it is also a container for data local to functions. So what is data local to functions? So basically, if you see any function body, then it has certain parameters or arguments. And for example, in this function factorial, there is this argument n, and in the main function, it has no arguments. And apart from the arguments, there are certain variables that are defined inside the function body, variables which are declared in the function body. For example, in this factorial function, there are no local variables, but this result variable in the main function, this variable is defined in the main function, right? So within this body of the main function, this result has been declared and it is a local variable, right? So basically every function has certain arguments as well as local variables. All of these are stored in the stack region, right? So the stack region will be used to store data which is related to each function, and within that we will specifically store the arguments, will store the local variables, right? So the stack section is used for the storage of variables which are local to functions or which are defined in the function body. Okay, this next point is that the stack section grows as function calls are made, right? So as you can see in this process address space, the code section and the data section, the size of these sections are fixed. They do not grow in size. The size is not variable. But the stack and heap section, they have variable length. So the stack section and heap section grow towards each other. So basically, when function calls are made, as the sequence or the chain of functions grows, the stack section grows downwards. For every function, we will put some information on the stack. And since there can be a chain or sequence of function calls, more and more data gets pushed onto the stack. So the stack will grow in the downward direction. And the point is that it is a section whose length is variable. And finally, in the same way the heap section also grows, we'll talk about the heap in the upcoming video. But for now, the point is that the length of the stack section varies during the execution, and as the function calls are made, its length increases. Also, when functions return, the size of the stack will decrease. When the function calls are made, the size increases. When the functions return, the size of the stack decreases. So guys, this was it that I had to talk about the stack section. Our discussion of stack, that is why do we need the stack, is complete. So this was it for this video. We talked about why do we need the stack section. We saw some code examples, and through the execution of those code examples, we saw that when a function is executing, it has a sequence of function calls, and the behavior that these function calls display is exactly the same as the stack data structure. That is why we need a stack section in the memory, so that we can replicate this behavior, we can simulate this behavior, we can execute the functions. So now that we have a understanding of why we need the stack section, in the next video we will see how is this stack section implemented, like how the function calls are represented on the stack, right? So this was it for this video. Thank you very much for watching, and I will see you in the next video. Thank you.